Welcome to UGC lecture series Linear Integrated Circuits. In this lecture, we are going to discuss about the active filters, types of filters, and they are low pass filter, high pass filter, band pass filter and band reject filter, their frequency response and derivation of the transfer function. A filter is a frequency selective electric circuit that passes the electrical signals of specified band of frequencies and attenuates the signals outside the band. The filters may be an analog filter or a digital filter. A simplest way to make a filter is by passive components such as resistors, capacitors and inductors. This works well only for high frequencies, that is the radio frequencies. At audio frequencies, the inductors become bulkier and heavy, and it is large, expensive also. For low frequency applications, more number of turns of wire must be used, which in turn adds to the series resistance, degrading the inductor's performance. Active filters overcome the problems of passive filter. It uses the op-amp as an active element and resistors, capacitors as passive elements. Op-amp filters have advantage that they provide the gain. The gain amplifies the signal, and so the input signals are not getting attenuated as in the case of the passive filters. Also, op-amps are used in non-inverting configuration, so it offers high input impedance and low output impedance. This will improve the load drive capacity, and the load is isolated from the frequency determining network. So, we have seen how the operational amplifier in non-inverting mode has the high input impedance and low output impedance in the previous lectures. Initially, so from that it has the active filter. If it has an op-amp in the non-inverting configuration, it has high input impedance and low output impedance. Active filters have their limitations also. High frequency response is limited by the gain bandwidth product and the slew rate of the op-amp. We know what is the gain bandwidth product and the slew rate. Already we have discussed in the previous lectures. High frequency active filters are more expensive than the passive filters. So, these are the limitations of the active filters, and the difference between the active and passive filters we have seen now. And next we move on to the different types of filters. They are low pass filter, high pass filter, band pass filter and band stop filter. As the name says, low pass filter which allows only the low frequency signals and which stops the frequencies other than the lower band of frequencies, and high pass filter which allows only the high band of frequency and stops the frequencies other than the specified higher band, and band pass filter which allows the band of frequencies which is specified and which attenuates the frequencies outside the specified band. Band stop filter also the reverse of the band pass filter. See the frequency response of the basic frequency response of all these types of filters: low pass, high pass, band stop and band pass filter. So, in x axis we have to take the frequency of the signal, and in y axis it is the gain in dB. If the frequency response have flat initially and it reduces after that, then it is actually the low pass filters response, because up to this it is actually the pass band, and after this it is stop band. I have drawn here the practical response. Actually, the ideal response have a sharp cut after the cutoff frequency. So, this is the frequency of the input signal, this is the gain in dB, this is the ideal response of low pass filter, this is the practical response of low pass filter. So, we have in ideal response we have the sharp transition between the pass band and the stop band. Say PB is the pass band and here this is the stop band. Similarly, the ideal response of high pass filter, you can have the stop band initially because it is going to allow only the higher frequencies of the specified signal. So, say this Fc says the cutoff frequency, and after the cutoff frequency all the frequencies signals are passed through this filter, and so it is the high pass filter. So, this band is pass band, PB refers pass band, and band pass filter, it has, say this is the lower cutoff frequency, this is the higher cutoff frequency, and this band is the pass band, and here these are the stop band. Always frequency of the input signal in the x axis and gain of the filter in the y axis, and this is the band pass filter. And the reverse of this band pass filter is band stop filter. Here you have pass band, here you have the stop band, again this is pass band, FL, FH. These are the two cutoff frequencies. FL is the lower cutoff frequency, FH is the higher cutoff frequency. So, here the specified band of frequencies are attenuated in band stop filter, and the remaining, the frequencies which are outside the band of specified band of frequency signals are getting passed through the filter. So, these are the ideal response of all the types of the filters. Why it is ideal responses? We have sharp frequency response for both the bands, pass band as well as the stop band of all the filters. So, what is the difference in practical response is, we will take the higher high pass filter. Since we have discussed about the practical response of the low pass filter, now we can take the high pass filter. Always take the frequency in the x axis and gain in the y axis, and the high pass filter's ideal response is this: initially the band of frequencies are stopped until the cutoff frequency, and from the cutoff frequency, the specified frequency, all the signals are passed through the filter. So, here initially it is not actually 0, it has a response like this, and after some time the response is constant, the gain is constant. Say A is the gain in dB, and here say this is the specified cutoff frequencies Fc, and this is actually minus 3 dB line. You can say this is A by root 2, it is minus 3 dB. So, here the rate of increase during the stop band is, for the first order low pass or high pass filter, it is plus 20 dB per decade. Instead of a 0 stop band, we have some signals which is allowed to pass through the filter, and that is the practical response of the high pass filter. Even in the low pass filter also, it is not simply 0, it has the frequency response in the stop band also. So, this is the way we the practical response of low pass and high pass filter behaves. So, here in the band stop and band pass filter, if you draw the practical response, then it will be like this. This is actually the, so if it is pass band, then it will first increase, and it has a constant response, then it decrease. Here it is this point which shows that it is A by root 2. and this is the response of the band pass filter. And band stop filter, first it passes, then it does not allow the frequency of signal to pass, and then it is the response of the pass band. So, here this center frequency is denoted as FO. Here this is FO. So, this is the frequency response of all the types of filters. The basic explanation we have seen, and for if we derive the transfer function of all the filters, then we can deeply discuss about all these frequency response of the filters. First, we discuss about the first order low pass filter. So, from the name itself, we have to come to know that if it is mentioned as first order, then the passive components connected in the active filter has only one set. Here, if you look at the circuit, this circuit has the low pass filter stage as R and C. This is the combination of R and C for the low pass filter stage, and this potential, that is the voltage across this capacitor, is the input given to the positive terminal of the operational amplifier. Since it is acting as a non-inverting configuration, the gain of the amplifier is 1 plus the feedback resistance divided by the total divided by the input resistance. So, it is 1 plus R2 by R1. This is the gain of the amplifier now. So, the voltage across the capacitor is the input given to the operational amplifier. So, now we have to find out the output voltage. So, since it is the low pass filter, this is going to allow only the lower frequency signals through this setup of R and C, and above the cutoff frequency, the signals of frequencies are attenuated by the same set of passive components. So, those output voltage, that is the voltage across the capacitor, will be amplified by using this non-inverting amplifier. So, since it is going to provide a high gain, even the voltage across the capacitor is very minimum, this amplifier will maximize or amplify the input signal at the output of the filter. This is the advantage of the active filter. And why this setup is called as the low pass filter? We know that the capacitor, or we know that the frequency is inversely proportional to the capacitive reactance Xc, X suffix C. So, F is inversely proportional to X suffix C. X suffix C is the capacitive reactance. So, if frequency is low, then Xc will be very high. Xc is the capacitive reactance. So, this reactance, if it is very high, then the capacitor in the loop will be acting as an open circuit. So, C will be an open circuit. So, if you check for the lower frequencies at the input of this particular circuit, and we know that Xc is very high for a lower frequency. So, this capacitance effect will be very high, and if it is very high, the capacitor will be open for the low frequency signal. So, whatever the input frequency is present, all the frequencies will be seen across the capacitor here. So, here Vi will be seen across the capacitor. So, the output is actually amplified output or amplified version of this input signal Vi. So, here this setup, this R and C setup is now allowing the lower frequency signals, and what happens, it has to be attenuate the higher frequency signal. So, if the frequency is very high, then the capacitive reactance is very low, and if the capacitive reactance is low, then the capacitor will act as a short circuit. So, if the high frequency is given at the input, this capacitor will be acting as a short circuit, no voltage across the capacitor will be seen. So, the voltage at the output of the filter will be 0 for higher frequencies. So, here if C is open, then V naught is equal to Vi, and if C is shorted, then V naught will be equal to 0. This is why the filter stages R and C component in the filter stage is connected in this way, or in the series for the input voltage, and to the other end of the resistor the capacitor is connected in shunt. So, this is the setup of the low pass filter. So, always when if the frequency is related with the capacitor, then we have to remember this formula. We know that the frequency is inversely proportional to the capacitive reactance. If the capacitive reactance is very high, then the capacitor in the circuit is treated as an open circuit, and if the frequency is high, the capacitive reactance is low, and the capacitor in the circuit is treated as a short circuit, and the remaining thing we have discussed now. So, for this setup, we have to calculate what is the transfer function of this particular circuit, and what is the response, frequency response of the filter, low pass filter, for the input frequencies, lower input frequencies and higher input frequencies. For this, first we have to calculate this voltage, say this is VA, because that is the voltage given to the positive terminal of the amplifier. So, at that time V out, that is the output voltage of the filter circuit, will be VA into the gain of the amplifier, it is RF, here it is R2 divided by R1. This is the gain of the amplifier. So, now what is VA? VA is the voltage across the capacitor. So, for which the input signal is given by using the potential divider rule, we have to calculate the voltage across the capacitor. So, Vi by Cs divided by the total passive components R plus C. So, I am taking it as R and Cs instead of R3 and C1. So, the voltage across the capacitor will be the input voltage into the capacitive reactance divided by the total. So, R plus 1 by Cs here. So, Xc you have to write it as 1 by Cs. Now, you calculate Vi by Cs divided by R Cs plus 1 by Cs. This will get cancelled. So, this is your Va, that is the voltage across the capacitor. Now, what is the output of the filter circuit? Va into 1 plus R2 by R1. I am taking this 1 plus R2 by R1 as A, and Va I am representing, I am substituting the value of Va which I have calculated here, Vi by 1 plus RCS, and now V naught by Vi is given as the gain of the amplifier divided by 1 plus RCS, and if S is equal to j omega. So, here we are representing the terms in S domain. So, substitute S is equal to j omega, and the transfer function now will be h of j omega, which is given as A by 1 plus j R C, omega is now 2 pi f. S is equal to j omega and omega is equal to 2 pi f. So, this can be represented as A by 1 plus j, keep this f as such, the remaining values R C 2 pi, you can take this as fh. So, where what is fh? Fh will be equal to 1 by 2 pi RC. Why it is called as fh? Here fh is the higher cutoff frequency for the low pass filter. So, this filter, this low pass filter is a filter that passes the signals with the frequency lower than a certain cutoff frequency. this certain cutoff frequency is the higher cutoff frequency. So, up to the higher cutoff frequency, the signals are getting passed through the filter, and after the higher cutoff frequency, the signals will be attenuated by this filter. So, that cutoff frequency is given by 1 by 2 pi RC here. The transfer function of the filter h of j omega will be equal to a by 1 plus j f by fh. So, this is the formula we have derived, and if we take the magnitude of the transfer function, because for the filter response we will be taking the gain in dB here. So, a gain in dB. Here the frequency of the input signal has been taken along the x axis. So, if you take the mod value of the transfer function of the filter, then it will be a by root of the real term square plus the imaginary term square. So, real term square is 1 plus the imaginary term square is f by fh the whole square. So, this is the modulus of the transfer function of the filter. Now, we can substitute the values of the frequency of the input signal. For the first time, if f is less than fh, say here is the cutoff frequency. For example, if we assume here is the cutoff frequency, and if the frequency of the input signal f which is less than fh, then here this from 0 to fh we can say. So, if this frequency is less, then if you substitute a lower frequency than this fh, then this term will be neglected because it is going to be a lower one. So, this term will be neglected, and what is the output of the gain in that case? So, the frequency response will be now modulus value is equal to A. So, here A will be the gain of the filter. Second, for the second case, if f is equal to fh, what is the transfer function of the filter? If f is equal to fh, substitute the value. If f is equal to fh, this will be equal. So, you have 1 here. So, a by root 2. A by root 2 is actually here, suppose this is actually, if you take it in dB, then it is minus 3 dB. Here a by root 2. If you calculate in dB 1 by root 2, then it will be minus 3 dB. And if for the third case, if f is greater than fh, then the magnitude of the transfer function will be, substitute the value, a greater value than this fh, then this the 1 will be neglected, only this term will be there, and if you take the root of the square term, then you have a greater value in the denominator of the transfer function. So, this gain will be divided by the greater portion of the denominator. So, now the gain is reduced. So, h of j omega, which is actually a lower gain. So, it is reducing here. So, this value is actually minus 20 dB per decade. So, how much it is reducing? The frequency response is reducing at the rate of minus 20 dB per decade. Decade in the sense, for every 10 times increase in the frequency, increase in the input frequency, then the gain is reduced at the rate of minus 20 dB per decade. So, this is the transfer function of the low pass filter, and this is the frequency response of the practical frequency response of the low pass filter. Now, if we want to make this frequency response similar to the ideal response, this is the practical response. If you want to make this response similar to a ideal response, then this decrease rate must be higher, because we have to have a sharp cut at FH. So, instead of having a minus 20 dB per decade, if you increase this decrease in gain rate, then you have to go for higher order filters. For example, if we go for a second order filter, in the circuit we have two sets of this R and C combination in this same setup. So, if we have a two set of R and C combination, then at the frequency response you have another minus 20 dB per decade roll off rate will add up. So, totally minus 40 dB per decade. So, if you go for the third order, again the next R and C pair will have another minus 20 dB per decade. In this way, if you increase the order of the filter, then the decrease in rate, or in the case of high pass filter it is an increasing rate in the lower frequency, will be added by 20 dB per decade for every pair of R and C. So, here just now I have explained with the transfer function of the filter the frequency response of the filter. So, here we have seen this is the pass band of the low pass filter, say LPF stands for low pass filter, and if this is the cutoff frequency, say it is 159 hertz, before the cutoff frequency all the signals are passed through the filter, and after this cutoff frequency no signal will get passed through the filter, and the decrease in rate is minus 20 dB per decade. And the next filter is first order high pass filter. So, we have seen previously the low pass filter, now it is a high pass filter. So, what is the difference in the filtering operation is the higher frequency signals only be passed through the filter, and the lower frequency signals, that is say the signals less than the cutoff frequency, will be getting attenuated by the filter. In the circuit, the difference between the low pass and the high pass filter will be, now here the resistor and the capacitor is interchanged. This is the only difference between the low pass and the high pass filter in the circuit, and we know that the voltage across this resistor will be the input to the positive terminal, and the other explanations are one and the same. And in the next session we will be discussing about the transfer function of the high pass filter and its response. So, in this class we have discussed about the introduction of the filter and what is the active and passive filter, what are the difference between these two active and passive filters, and what is the drawback of the active filter also we have discussed. And in the low pass filter we have discussed about the transfer function of the filter, how the filter works, how the filter allows the lower signals and attenuates the higher signals, and we have derived the transfer function of the low pass filter, and which is related with the frequency response of the filter. And in the next class we will be designing the high pass filter, and we will be discussing about the frequency response of the high pass filter. And try to answer these questions: what is a filter, list the difference between the active filter and passive filter, design a filter for higher cutoff frequency 1000 hertz. If the design is higher cutoff frequency and the filter is not specified, you know that which filter has to be designed. Higher cutoff frequency is given for the low pass filter, because after the higher cutoff frequency no signal will get passed, and before the frequency, before this higher cutoff frequency, all the signal will get passed through the filter. So, it is actually from the name it is reversed. If it is a low pass filter, then you have a higher cutoff frequency, and it is reversed for the high pass filter. These are the references. Thank you.